All right. I think time's up. So why not we just getting started? So hey, hello everyone. Good morning. My name is Xiang Sun. I'm an assistant professor uh, in the Department of Electrical and Computer Engineering at the University of New Mexico. So my research is primarily focusing on the wireless communications, free space optics, and area networks. So currently, I'm focusing more on the, how do we use reinforcement learning and federated learning to optimize the resource management, resource allocations in wireless communications, and how do we control the different UAVs such that they can, navigate through the air corridors, smoothly. So today I'm gonna talk about the free space optical communications for area networks. So this is the outline in general. The webinar comprises four major parts. First is introduction. We are going to talk about the concept of the FSO communications and some the attenuations that are gonna happen in the FSO link. And based on that, we can calculate how do we calculate the capacity of our FSO link. Then we're going to compare the performance between the FSO and the traditional radio frequency communications, such as the microwave and the millimeter wave. Then I'm going to talk about some two particular applications of using the FSO in the area networks. So one is for the area-to-area communications. We're going to use the FSO for the counter UAV communications, and the second application is for the ground-to-air communications, where we're going to use the UAVs to deploy the aerial base stations in the different like the disaster striking areas to facilitate the mobile networks. Then we're going to talk about some like the ATP system, the acquisition, position, and tracking system, which is a key component to mitigate the pointing loss for the FSO. So finally, I'm gonna spend some slides to talk about the how to achieve the full duplex FSO communications in the area networks. All right. So first of all, what is free space optical communication? So the history of the FSO can be tracked back to the ancient times when the smoke signals were used to transmit the information. So for example, the Native Americans, they used the smokes to communicate with the distant groups in their tribes. So for example, they would use those small signals to warn of the attacks from other tribes. So as the technology develops, the FSO communications was designed to, wirelessly transmitted data over optical beams, which is normally propagated through the air. So this figure just shows a very, very basic structure of our FSO communication. So we have in general, FSO transmitter and the FSO receiver. So first of all, the electrical signal is considered as the input of the optical transmitters, which is converted these electrical signals into the modulated optical signals. So the very basic modulation scheme is of keying modulations, which means that the absence of the optical beams indicates bit zero, and the presence of the optical beam indicates 1. So the modulated signal is transmitted to this the lens, the commutator lens, which is used to emit the optical signal to the air. And at the receiver side, the optical signal is first received by the optical collimator lens, and then received by the optical received optical signal is then demodulated by the optical receiver, and then to obtain the electrical signal. So very, very simple the schematic diagram here. So different from the traditional wired network. we where the optical beams is propagated through the fibers, right? We are very familiar with the optical fiber communication. But in free space optics, the optical beams is propagated through the atmosphere. So the optical signals may suffer from different type of the attenuation. So in general, there are 4 types of attenuation that degrade the performance of the FSO communications. So which are the scattering loss, turbulence, geometric loss, and pointing loss. So for the next few slides, I'm going to talk a little bit detail about how do we model those losses. So first, for the scattering loss occurs when the photons that is in the FSO beams collide with the particles in the atmosphere. So the optical beam will be absorbed and radiated through into different directions. So we can use this equation to estimate the scattering loss. So here L is the distance between the source and destination, and this sigma A represents the atmospheric attenuation effect. The atmospheric attenuation coefficient here. The unit is in dB per kilometer, meaning that this basically is determined by the weather. So we can see here that when we try to expand this the sigma A, we can see that the sigma A is determined by V and the lambda here. All right, Q is also a function of V here, we can see. So V basically means that it's the visibility range, and the lambda is the wavelength. So the visibility range V basically means the maximum distance that one object can be clearly seen, which is highly dependent on the weather condition. So for example, this figure just shows the relationship among the weather condition, the visibility range, and the attenuation coefficient, sigma A here. So the x-axis basically indicates the visibility in the kilometers, and it can be chopped into 3 different areas. If the visibility range is lower than, for example, 1 kilometer, we consider it is the fog condition. If it is between like 1 to 10 kilometers, then we consider it as haze condition. So if the visibility range is higher than the larger than 10, we consider it is a sunny condition. All right. So we can see here that the y-axis basically indicates the sigma A here, right? So we can see that as the visibility range reduces, the attenuation coefficient also reduces here. All right. So the reason why the performance of the FSO is so bad in the fog condition is because the size of the droplet in the atmosphere in the fog condition, this size is very comparable to the wavelength of the transmitted light. So which leads to a very inefficient scattering. So the second type of the attenuation is atmospheric turbulence. Right, so the turbulence normally happens due to the those index of the refraction is fluctuating, or it's changing very frequently. So this the index of the reflection fluctuation, which are caused by the the temperature, pressure, and the wind variations along the optical propagation. So this the variance of the refractive index will generate some eddies along the propagation path. So we're saying that if this eddies if it is large, for example, it's larger than the FSO beam size, then the FSO beam may deflect from the original path. So which is so-called the beam wandering. On the other hand, if those eddies that is generated by the the fluctuations of the refraction index is it's very small. Those eddies are very small. For example, if it is smaller than the FSO beam size, then the FSO beam would have some distortions in both intensity, very small distortions in both intensity and the phase. So in general, we can use these two equations to calculate. The first one is used to calculate the PDF of the turbulence loss. So I will not go over these equations, and most of the time you may see a different equation to calculate the PDF or estimate the PDF of the turbulence loss. So it is totally fine. And so the first one is to calculate the PDF of the turbulence loss, and the second one basically is to, based on this PDF, we can calculate the expectations of the turbulence loss, right? So the next type of the attenuation is the geometrical loss. So the geometrical loss occurs when the beam width here at the receiver is larger than the aperture size of the receiver. So meaning that some of the received optical beams may be the power of the received optical beams may be lost at the receiver side. So why does that happen? This is because we have this type, we will not always generate it's impossible to generate the parallel beams. So once the optical beams, getting emitted from the, transmitter side, we're gonna have the, this divergence angle. And because of this divergence angle, once the beam propagates through the atmosphere, the beam size is getting increased and increased and increased. So once this beam size at the receiver side is larger than the size of the length of the optical receiver, then, like I mentioned before, the portion of the optical beam is getting lost. So by definition, the geometric loss equal to the size of the receiver line, the receiver length divided by the size of the beam size at the FSO receiver side. So the last type of the loss is pointing loss. So the pointing loss occurs when the misalignment between the transmitter and the receiver exists. So this misalignment could be caused by, for example, the turbulence that I mentioned before, or the other reasons. For example, if your FSO transmitter and the receiver are building on the top of the two buildings, then the shake of the building caused by some wind would lead to the misalignment. So basically, as long as the center of the optical beams here is at the receiver does not overlap with the center of the aperture of the optical receiver, then the FSO link would suffer from the pointing loss. So here I want to mention that normally speaking, for each FSO transmitter and the receiver, the ATP system, the acquisition, pointing, and the tracking system will be developed to alleviate the pointing loss. So the function of the ATP basically is the transmitter is first acquire the location or the movement of the receiver and adjust its transmission direction based on the location of the receiver. So I will provide a more detailed design for these ATP systems later on. But one thing you need to know that even if we have the ATP system, we can only mitigate but not avoid the pointing loss, because the ATP system design itself would have some mechanical errors. So by estimate the mentioned four types of the losses: the scattering loss, turbulence, geometric loss, and the pointing loss, then we can calculate the received power based on this equation, right? So here the PRX indicates the received power, and the TX represents the transmission power. And then we can use this equation to calculate the capacity in terms of the maximum dead rate of a FSO link. So this EP is the photon energy, the amount of the energy can be carried by each photon. And this MB indicates the receiver sensitivity, which means that how many bits can be carried by each photon. All right. Now let's compare the performance between the FSO and the traditional RF communications, such as the microwave and the millimeter wave communications. So this table just provides the performance comparison between the FSO and the microwave links. So basically, we can conclude that the FSO can achieve a higher data rate over a longer distance. All right. So that's one of the advantage of the free space optics as compared to the traditional RF communications. Another advantage is that the FSO is conducted over the unlicensed spectrum. It's different from our mobile networks, right? 4G, LTE, and 5G. The users somehow need to pay those spectrum licensing costs. So because FSO is manipulate over the unlicensed spectrum, so the vendor do not have to pay for the spectrum licensing cost. And the third is the advantage of the FSO is since the spectrum used by the FSO does not overlap with any RF communication, so the interference from the RF will be negligible. And the advantage of FSO is reliability. FSO is considered as reliable communications as compared to RF because any interceptions and eavesdrop on the FSO link can be easily identified. Because optical beam is directional with a very, very narrow divergence angle, which is also a disadvantage of the FSO because of this directional features that makes the FSO link to be line of sight communication, meaning that any blockage on this propagational path of the FSO will lead to the communication failure. So another drawback of the FSO, which I have already mentioned, is it is very sensitive to the weather conditions. If, for example, current weather is foggy weather, then the performance drop of FSO link is very significantly. All right. So I see some conversations in the chat box. I probably may open this up at the end of the webinar. All right. So, all right. So next, I'm going to talk about some applications of the FSO communications. So the FSO has been widely used in the satellite to satellite communications and the satellite to ground communications. So I'm not sure that if you are familiar with the Starlink project, which is a project developed by the SpaceX. So the goal of the Starlink is to deliver low cost and high speed broadband internet to the locations where the current internet access has been unreliable or cannot be is completely unavailable. So the idea of the Starlink is that the company gonna launch a huge number of the low Earth orbit satellites, and these satellites are interconnected together, and each satellite is gonna serve a specific area of the Earth. So these interconnected satellites build a backbone, a network that is able to cover everywhere on Earth. So the solution for the satellite to satellite communications in the Starlink project, right now they are using this the Q band and Ka band, the RF communications. But there's a rumor here that for the next generation of the Starlink, they're gonna use free space optical communications to achieve the satellite to satellite communications. All right. So the FSO has also been used in the ground-to-air communications and air-to-air communications, as well as the terrestrial communications. For the terrestrial communications, the FSO gonna use the front hauling or the back hauling between the two base stations, or the back hauling between the two buildings. So for the later slides, I will concentrate on how does the FSO integrate into the into the ground to air and air to air communication. So our group has been working on a counter UAV project to control a group of UAVs to protect any places of interest against other like malicious UAVs. So these are places of interest, for example, could be the airport or the military base. So basically, there are two types of the UAVs. One is the pursuer and the evader. So the evader is used to enter this target area while escaping from the pursuer's the capture. And the pursuer aims to capture the evader in the alarmed area while avoiding the collisions with the other pursuers and the non-cooperative interactive entities, which is also called NCIE. So we have designed and trained a multi-agent reinforcement learning model where each pursuer runs a reinforcement learning model to determine its action based on the current states and the observations. So here the state means that the UAV's current location and the velocity, and the observation means the state of the other UAV's velocity and the location. And those UAV can be observed by the target UAV, which basically means that for we can achieve a distributed control, let the each UAV control its control and collaborate with the other UAVs. So this demo basically, let me see if I can, yes. So this demo basically showing the performance of the different, training time. So here the orange area is the target area, and the yellow area is the alarm area, and those are red. This red dot represents the evader, and those are the blue dots represents the pursuers, and the black dot represents the NCIEs, and also the pink area basically indicates the observation area of different pursuers. Right, and we have this iteration basically indicates the training iteration. A higher training iteration means that the performance of the model is much better. So the lesson we learned here is that the observation area is the key component to improve the capture rate. Meaning that if each pursuer has a higher observation area, then the capture rate is increased. This is because we don't have the centralized controller. So each UAV collaborate with other UAVs to capture the evader only if this UAV observe the evader. So if we can incorporate wireless communications, means that if one UAV observes the evader, it will notify the location of the evader to other UAVs within its one-hop communications. Then we can increase the capture rate. So we can see from this graph here, the result basically demonstrates this. So the y-axis is the capture rate, and the x-axis is the communication distance from 2, 4 to 10. So those are the relative values as compared to the area, right? So we can see that as the different color bars represent different methods that we use. So the method that we can focus on is the red bar and the green bar here. So we can see that here, as long as the communication distance increase, the capture rate really increases. So this really drives us to think about if we can use the FSO as the communication technologies to notify the pursuers about the existence or the location of the evaders, because as I mentioned before, FSO can achieve the longest communication distance as compared to the IF, right? So so the FSO can provide a high link capacity of a long distance. So to reap this benefit, we are applying FSO in the drone or UAV assisted mobile access network. So in the drone assisted mobile network, a drone is equipped with a small cell base station, and this drone can be quickly and flexibly deployed over any sporadic hotspot area like a traffic jam area, the concert or the football stadiums to provide high-speed wireless connections to the mobile users. Or the drone can be placed over any disaster striking area to offer the emergency wireless communications for the victims. So in our FSO-based drone assisted mobile networks, the data streams are first transmitted from the remote or the nearby cellular tower to a drone over the FSO link with very, very high data rate. And the drone can convert this received optical signal into the RF signal and then transmit the RF signal to the corresponding mobile base stations, mobile users. So we have conducted some analysis and simulation in the context of the FSO-based drone assisted mobile networks. And we found that first, the capacity of the FSO link as a backhaul or the front haul, depending on the baseband unit, where the baseband unit is located. So this FSO link capacity is sufficient for the access network under the assumption of if the current condition is haze or the sunny condition, and the second assumption is we just simply ignore the pointing loss. All right, meaning that we don't have to worry about the bottleneck happens on the FSO link. All right. So also we found that the placement of the drone matters. The placement of the drones may significantly affect the performance in terms of the spectrum efficiency of the users. So these are 4 figures basically shows the spectrum efficiency distributions in an area. This area is served by a micro base station and the drone here. So the first figure is a case that we only have a single micro base station that is deployed in the 500 location here. And the rest 3 figures shows the different UAV deployment, which generates totally different spectrum efficiency distributions. So if we want to maximize the overall spectrum efficiency, we can find that this placement where the drone is placed over around 800, 500, and the altitude is 86. If we place the drone over this location, then this placement is the best, which is going to generate the highest overall spectrum efficiency among this area. So, we previously mentioned that the capacity of our FSO link is sufficient for the access network if the pointing loss is negligible here. So here the question is whether the pointing loss is negligible as compared to the other losses, right? So here we try to evaluate the pointing loss of our FSO link. So I've mentioned that the ATP system is always used in the FSO communications to mitigate the pointing loss. So here we designed a cost-effective and a lightweight ATP system for the ground-to-air communications. So in this ATP system, the drone here is only need to equip with only a single beacon emitters like the laser or a pointer, and at the base station it has the camera mounted on a gimbal, which is controlled by the controller, and also we have the FSO transmitter at the base station and the receiver at the drone here. So the camera is used to capture the beacon signals sending from the UAV, and the controller is to analyze the beacon signal in the image to understand the relative positions of the UAV, and then adjust this gimbal accordingly to reduce the pointing loss. So basically, the function that achieved by the controller comprises four parts. So the downsampling basically is to reduce um, to decrease the sample rate to generate a new field of view image with a low resolution. So the purpose of the downsampling is to reduce the latency of the image processing later on, because the frequency of the controller to adjust the gimbal is should be maybe very fast depending on the velocity of the for the UAV. So the second function achieved by the controller is the image filtering. Basically, is to convert RBG image into a binary image. And the third function is the displacement identification, which we basically try to calculate the displacement or the distance between the center of this beam spot and the center of this of the camera's field of view. So based on this displacement, we're gonna use the PID control algorithm to calculate the velocity of the gimbal. How do we adjust the direction of the gimbal based on the displacement? All right, so we have conducted some experiments to evaluate the pointing loss, and here are the settings. So this is the portion is the base station side. We have the camera, the transmitter, and the gimbal, and the corresponding controller here. So at the receiver side, we do some manipulations. So for the UAV, we use this rotate gimbal, or the rotate stage gimbal, which is equipped with a beacon to emulate the behavior of the UAV. So basically, the beacon is first reflected by the wall and then captured by this camera. So basically, the beacon spot on the wall, which is used to emulate the trajectory of the UAV or the movement of the UAV. So the reason to do that is we can well control the velocity of the UAV. If we want to make the UAV's velocity to be constant, then we just making sure that this rotation stage is moving at constant speed. So here is the demo video. And one thing I want to mention here is that the red dot represents the beacon signal, and that indicates the location of a UAV's movement. And the green dots is the FSO being transmitted from the base station to the UAV. So the goal here is that as the red dot moving around, the green dots need to be adjusted accordingly to keep the distance, the same distance to the red dot. So we have the three. So in the videos we have three parts here. This portion basically shows the video or the image captured by this camera, and those are two parts indicates the angle of the angle of displacement in the pan and the tilt direction. And during the whole experiments, we just gradually increase the speed of the UAV in terms of this red spot to see what's going to be the pointing loss on the different speed. All right. So let's move forward. So those are two figures just shows the angle of displacement, over time when the speed of the UAV is in this figure is 2 meters per second, and in this figure it is 10 meters per second. So the whole time duration basically is to keep track of the angle of displacement in the pan and the tilt direction for one trajectory. Means that the red spot is moving from one end toward the other end of the line. All right. So we can see here that from one end to the other end of the line and go back to the original end. All right. So this is the whole trajectory. So here we can see that there are how many portions of the stage. So first, the UAV in terms of the red spot is static. Then it has an acceleration stage to accelerate its speed from 0 to 2 meters per second, and using the constant velocity to move towards the other direction, and it has a deceleration stage to adjust its the velocity from 2 meters per second to 0, and then it's getting stable, and then acceleration go back to the starting point. Also, we have the acceleration and the deceleration and the constant speed stage here, right? So the same thing happens for this, when the velocity is 10 meters per second. So from here, we can find that the angle of the displacement oscillates gently when the velocity is does not change, means that the k is equal to 0 meters per second. And the displacement may significantly change when the beacon is in the acceleration constant and the deceleration period. Also, the speed of the UAV affects the angle of the displacement. A higher speed leads to the higher angle of the displacement. Also, we also observed that the angle of the displacement in the pen is smaller than the displacement in the tilt. And this is probably because the mechanical design of the gimbal, which we are using the DJI Ronin S gimbal. This design, in this design, the pen axis is much stable than the tilt axis. So that's probably the reason why we're gonna generate a higher, a higher displacement in the tilt than in the pen.
Wow.
So to avoid the performance uncertainty during the acceleration period, we measure the angle of the displacement when the beacon is in the constant speed. So the first two figures are the box plot of the angle of displacement in the pen and tilt directions respectively under the constant speed. So we can see here that the x-axis basically represents the speed, and the y represents the pen and the tilt displacement. And the result in the figures basically also demonstrate that the angle of the displacement increase as the beacon velocity increase. So this last figure shows the average displacement between the center of the optical beam and the center of the FSO receiver. And this x-axis is the velocity, x is the distance between the drone and the base station, basically. And this color bar represents the average displacement, right? A higher, more darker color means that the displacement is low, and more brighter means the displacement is high. All right. So it's not surprising to see that this displacement is monotonically increasing with respect to the velocity and the distance between the drone and the base station here. So we first analyzed the average pointing loss of the FSO link by applying the ATP system. So those are three figures just to show the value of the average pointing loss by applying the designed ATP system when the divergence angle here in the first plot is 2 millirad, 1 millirad, and 0.1 millirad. All right, and here the y-axis is the distance between the UAV, the drone, and the micro base station, and the x-axis again is the velocity. Right. And from those three figures, we can also derive that the design ATP system is enough to generate the low power loss to establish the FSO-based front hole link when we apply the large divergence angle. Oh, by the way, if you forgot the definition of the divergence angle, basically it's here, right? It's determining the size of the optical beams transmitted from the transmitter, right? So again, these graphs, those three graphs, we are applying three different divergence angle: a large divergence angle, medium divergence angle, and three small divergence angle. So if we apply the large divergence angle to carry the data and and transmit it to the base station, we can see that if the pointing loss is really negligible if we have the velocity is less than 5 meters per second, or if we apply this small divergence angle optical beam, and the distance between the drone and the UAV is short, like it's less than, for example, 400 meters. In this diagram, we can see that the pointing loss is really negligible. So whether or not the design ATP system is enough really depends first the distance between the drone and the drone and the micro base station. Second, the velocity of the UAV, and the third, the divergence angle of the optical beam. All right, so now we have analyzed the pointing loss of the FSO link when ATP system is applied, and the drone can only need to equip with a single beacon signal to a beacon emitter to indicate its location. But however, each FSO link needs to have ATP system to mitigate the pointing loss. So the problem is that if we want to achieve the full duplex FSO communications, means that we need to have at least the two FSO link need to be established between the drone and the micro base station. Then we need to implement two ATP systems, meaning that the drone need to equip the one additional FSO transmitter and one gimbal, one camera, and one controller to achieve the FSO to achieve the ATP system for this uplink communication. So this really poses a challenge to the drone because the payload capacity of a drone is very limited, and the drone can normally carry less than, for the current commercial drones, the payload capacity is normally less than 10 kilograms. Most of the drones are just around 5 kilograms, basically. And the gimbal that we use, on the other hand, is very heavy. So we use the DJI running as a gimbal, and its weight is around 4.2 kilograms, I would say. So if we add some camera, the computing board, and the FSO transmitter, the total weight would be close to 10 kilograms. So it's really very hard for the drone to carry so many components and take off from the landing pad. And also the energy consumption of the drone is going to be increased if the capacity or the payload of the drone increases. So we really want to reduce the payload of the drones. So what is the solution to solve that? So one of the solutions is that we can use modulated retroreflector, the MRR-based the optical transceiver to reflect part of its received optical beams. So basically, for the downlink, the base station gonna send this optical beam carrying the downlink data to the UAV, to the drone, and the drone gonna use this MRR. First, it's gonna split this downlink optical beams into the two portions. One portion gonna go to the optical receiver to demodulate the data from this optical beam, and the other portion is gonna send to the MRR, which is gonna be reflected and remodulate these optical beams based on the data from the users. So basically, the drone does not necessary to generate its own a new optical beam, but only it can reuse these downlink optical beams to remodulate the data on these beams and consider these new beams as uplink. Right. So once the micro base station receives this uplink optical beam, they're gonna send to the optical receiver to demodulate the data that carried by this uplink. So in this case, we can see here that first, the drone does not necessary to um, equipped with the cameras, the gimbals, and the computing board anymore, right? Meaning that it's not necessary to have the whole ATP system mounted on the drone. Because if we achieve, if we implement the ATP system at the base station to make sure this downlink FSO beam is well aligned, then the uplink optical beam is automatically aligned because this is a reflected beam. All right. So by doing so, we can significantly reduce the payload of the drone. All right. So I will not go through the details, but if you want to understand the detailed design here, this is a reference paper. You can look into that. All right. So that's all for my presentation. I think I can start to answer the questions in the chat box. All right, so I think I can put it here. So the first question is the new Starlink satellite, which has been launched recently. I already used. Oh, good to know that. I already used the FSO link. Right. I think the previous satellites, as far as I know, they use the Q band and the K band, but I have heard that the next generation they're going to use the FSO link. But it's glad to hear that for the current implementation they already use the FSO. So the second question is FSO at a very narrow beam. How do you keep the communication link working on the moving UAVs? All right, so to answer this question, I think probably the question is from the previous, very beginning of my presentation. So we're going to use, basically to solve this one, we're going to use the ATP system, right, to adjust the direction of the optical beams based on the received beacon signal sending from the base station. But again, the performance really depends on the movement of the velocity of the base station and the distance between the velocity of the drone and the distance between the base station and the drone. So one more thing I want to point out is that, so this design here, we just achieved, a coarse granularity alignment. So if you look at the ATP systems for for example, ground to satellite communications, they have a fine alignment system that has already been integrated into this ATP. And this also a fine alignment system is hardware based, which means that they're going to use the so-called PSC phase shifting detector. I forgot the full name for that, to fine tune these the gimbals or the switch millers to make sure that the FSO transmitter is aligned with the receiver. Right. So the next question is for UAV being alignment will be a big issue regarding the UAV. Plus number 13. Yes. All right. So like I mentioned, I think most of the audience are worried about the alignment. That's true. I mean, the big challenge for implementing the FSO in the area communication, in the area network is alignment. So that's why we try to evaluate the performance of the ATP system. And yes, it is correct. The alignment is one of the most important topic in the FSO-based aerial communications. All right. Could you please explain one of your solutions to reduce the load? Okay, 20. All right, so the explanation basically in the slide 21, right? Meaning that, so if we have the, two pair of the FSO transmitter and the receiver here, right? meaning that we need to design we need to have the two pairs of ATP system. One ATP system is for the downlink, the other ATP system is for the uplink, right? So for the uplink, if we want to implement the APP system, the drone need to, have the camera, the gimbal, and the controller, right? So the solution is that instead of, design an independent optical beam, right, for the uplink, we're gonna reuse this downlink, right, by, reflect this downlink optical beams to the base station, right? So this uplink optical beams basically is a reflection of the downlink optical beam, right? We just reuse its the laser power to modulate the uplink signals here. So in this case, if this downlink is well aligned, then the uplink will be automatically well aligned because again, it's a reflection here, right? The direction of the downlink is the same as the direction of the uplink. So by doing so, we only need to let the base station equipped with the ATP system, right? The drone does not need to have the ATP system anymore, so which can reduce the payload of the drone. All right. So as per your slide solution in slide 21, there will be battery power saving of UAV. Right. So it's not necessary. So basically, the solution here indicates that the payload of the drone is reduced as compared to the previous solution when we have the two independent optical beams, right? One for downlink, the other one for uplink. So in this solution, we only have the one ATP system, which can reduce the payload. So if the payload of the drone reduces, and the energy consumption of the drone gonna be reduced. So that's the basic idea. Right. So for some papers, they try to let the drone to equip with some like the solar panels, which basically is try to increase the capacity of the battery, right, by recharging the batteries of using the green energy here. So which is another solution to prolong the battery life of the drone. Some papers they use FSO to transmit energy and the data stream simultaneously, but they need to increase the transmission power of the optical beams a lot. Right now, the transmission of the optical power here in our example is normally like 5 milliwatts, maybe even 1 milliwatt, which is not enough to transmit energy. Once you receive this less than 1 milliwatts power at the receiver side, then it's really negligible. So the idea is that they're gonna use maybe 10 watts energy as the transmission power of the optical beam. So in this case, it may be possible to sustain or prolong the battery life of the drone. But the bad side is that it's not safe anymore. You're carrying a weapon, basically, the optical weapons, sending high power lasers to the drone. So there's a pros and a cons. All right. I think there's no further questions in the chat box.
Yeah. So thank you, Xiang, for a wonderful presentation. And if anyone, if you are a member, it's for the audience. If you are already a member of VTS, it is great. But otherwise, you are welcome to join the VTS VT Society. And the presentation, along with the slides and actually the video itself, will be available on the website that was posted on the chat message. So thank you again, Xiang, and we can wrap up. Have a good rest of the day.
Thank you, Kamesh. Thank you for having me here. And thank you. Take care.